of this course. So in the first two sessions, we discussed about modulation format and transmitters. The last session, we discussed about receiver and DSP. And today we are going to discuss about a spectral shaping or a spectral pre-emphasis, forward error correction, and recent modulation techniques. So just to recap the first session, we discussed that the global data traffic increases every year. And to support such data traffic in the fiber, we must increase the fiber capacity. Now, since the number of channels are limited, so only way to increase the fiber capacity is if we can increase the spectral efficiency. This means if we can try to send more and more data per optical bandwidth, we can increase the overall capacity. And that can be possible by moving to the higher order modulation like QPSK, 8 QAM, 16 QAM, etc. And then we discussed about how we can generate such higher order modulation format using the IQ modulator. And then last session we discussed that what happens if we transmit those higher order modulation systems to the DWDM system, which consists of amplifier and fiber span. So when we transmit the higher order modulation, what happened that the symbol gets corrupt because of dispersion and nonlinear effect in the fiber and various other effects like phase noise from transmitter, receiver, sort and thermal noise, etc. And the received symbols are highly corrupted through the phase and intensity noise. And in order to fetch full recovery of the original data stream, what we sent, what we need to do is we need to convert this corrupted constellation diagram, or let's say corrupted symbols, into the original symbols, and then from these original symbols we can recover back the bits. And so one of the function of the receiver is basically to purify the corrupted signal and make it looks like very pure, independent of free and intensity and phase noise, and then we can recover the bits. That's the main function of receiver. And we discussed that there are various type of receiver, direct and coherent detections. Coherent is preferable. And then we discuss also that inside the coherent we have homodyne, heterodyne, and intradyne receiver, depend upon what is the local frequency, and intradyne is preferred in this case. And in the intradyne receiver, all the commercial transceiver, what they use is digital coherent receiver, which employs some algorithm, for example, VNV algorithm, to remove the phase error or what is called digital phase estimation. So by phase estimation, they can actually estimate what is the phase noises and remove it from the signal. During this process, because of the computation, we add some errors due to cycle slip and phase ambiguity, and this contribute to the bit errors. So all this we discussed in the last session, and today we are going to discuss about uh, more detail about little bit about transmitter side, the DSP of the transmitter side, uh, specifically the spectral shaping as well as spectral pre-emphasis, which we see in most of our transceivers. Also, we are going to discuss about forward error correction, what are the uses, and what they mention in the data sheets, and then most recent modulation formats. So let's start with the DSP transmitter. So not only at the receiver, but also DSP transmitter employ heavy DSP. There are various purpose of DSP in transmitter side. One of more important is converting those bits into the symbol, depending upon what higher order modulation format we choose. So we call it digital logic implementation to create the constellation diagram, and various other. But we are going to discuss something about impulse shaping and spectral pre-emphasis, as well as forward error correction generation. So if you see at the DSP site an IQ modulator, this is the usual modulator used in the commercial transceivers. So we have a data and we convert this data to the higher order modulation symbols through some logic implementation. And after that, this symbol must go to the MZM Mach Zehnder modulator to create this constellation diagram or the higher order modulation signals. So this modulators are driven by voltage. So we must convert those symbols into the voltage level. So they use what is called level generator, generate a certain level. And then we use something called IS, impulse shaper. The purpose of impulse shaper is to convert this voltage into the optical signal, and this optical signal output depend upon what voltage is coming here. So the shape of the voltage determine the shape of the optical signal which is going to transmit into the fiber. And the shape of the optical signal determine the performance of those signal, or let's say performance of the channel in the network, because the nonlinearity overall depend upon how the channel shape or the spectral shape looks like. And because of that, we need to shape the voltage level. And we do it by using DAC, digital to an analog converter. So there is a DAC in the transmitter side. What it does is basically it create the Gaussian type of voltage shape, because the Gaussian voltage shape convert into similar optical shape, and which has the Gaussian shape has the best nonlinear performance. So maybe close to Gaussian shape, not exactly the Gaussian shape. So basically we have these level generators voltages, and then we put it to the DAC, and DAC convert this spectrum, and that's going to transmit through the optical fibers. Now, if you closely look at it, the bandwidth of the signal which is generated by the transmitter has bandwidth greater than the symbol rate. So this is the symbol rate, so it's greater than the symbol rate. And if the bandwidth is greater than the symbol rate, this means efficiency is very low. So in order to get best possible efficiency, we must keep the bandwidth equal to the symbol rate. So we must restrict our transmitted signal spectrum inside the symbol rate. And in order to do that, what we use is filtering. So we filter the whatever generated spectral optical spectrum through the Nyquist kind of filter, which restrict the signal in this domain. So usually what they use is something called raised cosine FIR filter, and this filter basically filter this spectrum and create this kind of spectrum shape. This kind of a spectral shape has a bandwidth very close to the symbol rate, so it has optimum spectral efficiency. And this is what we encounter in general whenever we have a new transceiver. We check through the optical spectrum analyzer, and usually we see such a spectrum of the transmitted signal. Now, this spectral shape depend upon what kind of filter you choose. So we use usually a raised cosine filter, and the generated channel bandwidth is equal to 1 plus beta times symbol rate. The beta is called roll-off factor. It defines how the edges are. So if edges are very sharp, this means beta is 0. If edges are smooth, then beta has some value. So if beta is 0 means edges are very sharp, this means it's a rectangular. And so if it is soft function, it means that the performance in terms of nonlinearity is very, very bad, because it's create a chirping effect. So usually beta is not considered taken as a 0, so it's not rectangular but certain shape. So because it's a trade-off between the spectral efficiency and the nonlinear performance. So if beta is 0, spectral efficiency is very high, but if beta is non-zero, the spectral efficiency is low, but nonlinear performance is better. So there is always a trade-off between the spectral efficiency and the performance of the channel in the presence of fiber nonlinearity. So usual value of beta is chosen as like 0.2, 0.3, etc. So this is the shape we are familiar with, but there is another properties of the channel shaping or channel spectrum, which determine the performance in terms of transmission of signal through the filters. So for example, the filters usually deteriorate the signals, right? So every channel pass through number of ROADMs, and ROADMs has many filters. So the filters filter out the edge of the channels. So if it cut the edge of the channels, basically what happened after it passed through a lot of filter, as you can see here, I try to plot a diagram after many filter. What happened that the bandwidth decreases. It means it create the OSNR penalty after a few filter. So because the filter usually affect the edges, it cuts the edges. So because of cutting the edges, you have a OSNR penalty in presence of ROADMs in the network. So in order to avoid those penalty, what we usually do is boost this higher frequency, and we call it a spectral pre-emphasis. So a spectral pre-emphasis basically boosts these edges, and so its boost edges means it's create higher amplitude, and it looks like a bad signal. So different transceivers provide different kind of SP. Some of them may not provide also, but some of them provide this. So these are various different level of SP can provide it, and then we can see that with the higher SP level, you have lower and lower OSNR penalty. So these are the use of a spectral pre-emphasis in the channel. So if I'm going very fast, you can always stop me and ask anything. So next one is forward error correction. Yeah.
So the spectral Set-Partitioning is part of the DAC circuitry, or is it provided by the DSP chip, like
No, it's not
dynamically?
it's not part of DSC. It's a different circuit for that.
Okay.
Abhishek, one more query on spectral preemphasis.
Yeah.
This particular phenomenon is applicable on what rates? 100G, 200, I mean, in terms of specific rates.
Okay,
I-
so it depend. Okay, so it depend upon what channel bandwidth you are selecting, right? So it depend upon the filter. For example, if you are, let's say, you are choosing 42 gigabaud channel, right? So 42 gigabaud channel means your bandwidth of the signal is almost 40 or 42 gigahertz, and you are passing it through the filter or ROADM with bandwidth 50 gigahertz, and the real bandwidth of the 50 gigahertz is around 38, 39, or maybe 40. So it cut the signals. Okay, so you need to always choose a compatible bandwidth, right? So when we select 50 gigahertz channel, we usually go for a ROADM with 50 gigahertz. If you take a higher bandwidth of ROADM, you won't see this edges cut. So there is no use of SPE then.
Okay, so this is directly relating to the let's say channel bandwidth, not only spectral bandwidth, but also the channel size. Let's say 100G, 200G, or 400G channels that we
It's
use.
related to the baud rate, yeah.
Yeah.
It's related to
Okay.
the baud rate and corresponding baud rate, what filter you are applying. Let's say if you
Okay.
are choosing a baud rate 69, right, or 67 point something, and then you are applying a 100 gigahertz filter. So 100 gigahertz filter has a effective bandwidth of 75, 76 gigahertz. So entire channel will pass through it, and there is no cutting of edges.
Okay.
So in
Okay.
that case, there is no cutting of edges. So SPE doesn't perform anything. In fact, SPE in that case provides some penalty, different penalty. So
Okay.
so.
Okay,
Yeah.
Abhishek. Thank you.
In most of the newest new transceiver, they don't have the SP feature because they don't need it. So it's not necessary that in all of the transceiver you see. In some of the transceiver you see this SP feature.
Not
Okay,
meeting
Abhishek.
some
Yeah.
training. It's training, man.
Sorry,
Talent. Is it?
I couldn't hear you. Can you repeat?
No, he was not on mute, so I
Okay,
muted.
sorry.
Okay.
Okay, sorry, I thought somebody has something. Okay, anyway, so I just also want to mention that another function of SP is also the nonlinear effect. I'm not mentioning here because the nonlinear effect also affect the edges. So most of the nonlinear effect, if you analyze the spectrum, the nonlinear effect mostly lies at the edges. So SP is supposed to improve the nonlinear characteristic as well, but most of the network has both filter and ROADM and nonlinearity. So because the filter already cuts these edges, so we don't see improvement in terms of nonlinear performance. But but there is another use of these edges for SPE for the nonlinear performance as well. We don't observe in our network. That's why I didn't mention it here. Okay, so next one is forward error correction. So why we need a forward error correction? So last session we discussed that whenever we transmit higher order modulation formats, what happens? The symbol gets corrupted through the noise, nonlinearity, dispersion, etc. And the receiver try to remove it, and it employ various compensation method. I mentioned in the table the source, how it affect, and how receiver remove it. You can go through it later on. But even if receiver try to remove those noises, still there is residual noises or residual distortion present in the symbol because of some ineffectiveness of some limitation of the DSP as well. And so there is always a bit error present, even though there is a receiver try to remove those noises. So there is always some bit error present, and as long as the bit error is below certain threshold is fine. But sometimes the bit error is very high, and then you can't lock a transceiver. So you need to reduce the bit error so that we can lock the receiver, or you can say that you can faithfully recover the original bits. So for that purpose, we need to reduce the bit error rate or reduce the bit error, and for that purpose, we use fake. So fake is forward error correction, which is applied at the transmitted signal or transmitted bits, and it try to reduce basically the bit error from very high value to very low value. For example, maybe 10 to the power minus 2 to 10 to the power minus 15, almost error-free correction. So this is in terms of bit error. So it reduces the bit error rate. So the idea is the fake is going to reduce the bit error rate. But in terms of the the physical or let's say what is available in the optical network, how it affects the network. So in terms of the real monitoring parameter, for example, let's say OSNR. So it reduces the OSNR required it's relax the OSNR required by certain transceiver. So for example, if there is no fake, so required OSNR, for example, 16-com modulation format for certain transceiver, it could be 25 dB. So unless you have 25 dB OSNR, you may not able to demodulate or recover the data from 16-com. And so it requires very huge OSNR. You can't transmit this for high symbol rate, or you cannot transmit it for longer distance. So it has very limited feature. So once you add fake, what it does, it reduces the bit error. In other words, it relaxes the OSNR requirement. So instead of 25 dB, you may need 16 or 17 dB OSNR. So this means even with the lower available OSNR, you are able to recover the data. So you can transmit for longer distances or transmit for higher data rate, higher symbol rate. So one of the effectiveness of fake is it reduces the OSNR penalty or OSNR required by uh, commercial transceiver. So it increases the transmission distance. How fake work? So fake are actually parity check codes. Parity check codes are like it's kind of a Hamming code, or there are many kind of the parity check codes. What it does that it can detect or correct the errors occurring in the information bits. So we have information bit, and when it passed through the fake encoder, it added some redundant bit, or we call it overhead. So this overhead bit, it is usually a Hamming code or RS code. There are many different kind of code, and this additional added of code try to find out where are the error and try to correct those error. So that's the functioning of fake. Now, since we are adding some bits which are extra bits, which has no information, so we call it overhead, and total word is payload is information plus overhead is called code word. So we basically transmit the code word which contains some redundant or overhead bits. And when the error occur because of nonlinearity and dispersion and phase noises, etc., it try to find out where is the error and try to correct those error. So received bits with the error is fed to the fake decoder, and decoder work with this overhead and try to recover the bits or try to correct the error. So there is two terms, something that's called Burr prefake and Burr postfake. So Burr prefake is without the fake work, what was the actual Burr and how the Burr is reduced. So it's called postfake Burr. And we are going to see some terminology based on this. So some terminology of fake is, one of them is code overhead rate. So code overhead rate is how much extra or redundant bit you add into 100 divided by total bits. So that is total. That's the code overhead rate. And in many data sheets of many transceivers, you can see some value of it. For example, 15% overhead for the new module AX1200. It support up to 400 gigabaud. So here you can see the overhead is only 15%. So what number is actually good, 15%, 10% or something? It depends upon how performance of the fake itself. So since we are adding additional number of bits, an additional number of bits has no information, but it still is going to occupy the bandwidth. So we are able to correct the data, we are able to reduce the Burr, but at the cost of extra additional bandwidth, or at the cost of reducing the total information we can send through the fiber. So at that cost, we actually try to recover, try to correct the bit error. So as low as overhead is good. So here is 15%, but as low as low overhead is good, as long as it can correct the bit error at under certain threshold level. So another term we use is called coding gain. Coding gain is related to how the Burr is changed, and Burr is can be defined as a Q factor. So how the Q factor is improved after the fake and before the fake, and that difference is called coding gain. But now remember, the coding gain, we must also take care of the additional bandwidth we use for this overhead non-information bits. So if you take account of that additional bandwidth we used, we call it net coding gain. So it's coding gain minus this value. And in the most of the data sheet, you can see the value like 11.1 dB for certain modulation environment for some transceivers. Similarly, there is another term, pre-fake Burr threshold. So even the fake try to reduce the Burr, but it has a limitation. It cannot reduce the Burr if Burr level is too high. So there is a threshold level. Up to that threshold level, it can reduce the Burr. If the Burr is very, very high, even the fake won't work and won't give you the error-free transmission. So because of that, it defines a threshold level for error-free fake transmission, which is determined by net coding gain as well. For example, most of the transceiver has around 2e minus 2. Here for Acacia, the new module has 2.4 e minus 2. So these are the terms actually we see if we read the data sets and compare the different vendors, what are their fake, what is overhead, what is net coding gain, what is Burr threshold, etc. And then we can see which one is better or not. So the next one is the decoding decision. The fake itself doesn't work alone. Fake itself work how the decoding decision is done. And what is decoding decision? So if you remember this diagram from the last session, that we receive the data, we convert into the I and Q current and try to remove the phase noise and intensity noise, etc. And we try to get this pure I and Q symbols, which is a higher order modulation format symbols. So we try to get I and Q current, and from I and Q, we try to recover the bits. And we need to provide certain thresholds to decide whether the symbols belongs to this or other. So we try to recover the bits from the symbol. And that recovery is called decoding decision, how we decode to the original bits. So how this decoding decision is done is affect the performance of the fake itself. So often the decoding decision and fake work together. So whenever we see certain fake, we also see which kind of decoding decision has been done. And both work together, so both come together. So let's see some of the decoding decision. So there's two kinds of decoding decisions. One is called hard decision decoding, another is called soft decision decoding. I'll just give you an example, which may not be like practically correct because we use phase modulation, but just to understand, let's see, we are transmitting these symbols, these four symbols. And hard decision is done based on a very fixed threshold, only one threshold and very fixed threshold. So for example, if you transmit these symbols, let's say symbol duration of 0, bit duration of 0, or symbol duration of 0, you have no laser power, and in 1 you have some laser power. And because of the non-linearity, dispersion, noises, etc., you obtain some power at the receiver end where it's supposed to be no power in that duration. So when it passes through the photodetector, you have some current. And then we apply a threshold. So if you apply a threshold, but whatever the above, if the current is present, we have a bit decision of 1. If it is below, it's 0. But because of the noise and etc., we receive a 0. We receive some current in the bit duration of 0. So at the end, we are able to make a hard decision and say that it was not 001, but 011. And then we try to compare from the whatever transmitted and see what is the Hamming distance between the transmitted and received one, and which one have the lower value. There is a chance that that received bit belongs to that one. So here, three of them has smallest value. So there is a 33% chance that you can make a correct decision. So the chances are very, very low in hard decision, and error is very high in this case. So we can move to the soft decision. So what is soft decision is, it takes multiple threshold and it takes use a very complex algorithm to make a decision, whether it's 0 or 1. But even it doesn't say whether it's 0 or 1, rather than it say what is the chances of having 0 and 1, high probability, low probability, or moderate probability. Since now we have in coherent risk transceiver, we have a DSP, so it can make use of DSP processors to implement all these complex algorithm to make a soft decision. Again, obviously accuracy is very high because you have multiple threshold level. So for example, one of the case, in the same case here, they use the current level for received bits, and then they try to find out what was, if originally transmitted, if you pass it through the photodetector, what was originally transmitted current, and then try to find out the Euclidean distances, some mathematics, and then they try to find that where the small distance is there, that's the high probability of having that symbol. So for this case, 001 has a very small distance, so it has very, very high probability that transmitted symbol was 001, even though there was noises present in the 0 duration. So it gives very high probability of accuracy, but it doesn't give whether this is this symbol or other symbol. Instead, it gives the probability. So higher chances that the transmitted signal was 001, and others has very low chances, but they still have chances with lower probability. So accuracy is higher, but it has multiple threshold level. So we need to perform multiple threshold level. And so how we can create multiple threshold level? So the fake must know what was the threshold level used during the decision decoding. So for the SD decoding, the soft decision decoding, they use something called reliability bit or the quantization bits. And these are the additional bits provided to the fake to show that how many level of threshold was there, to see what are the level of accuracy was there. So the soft decision fake create multiple level of threshold, and so multiple bits for what is called reliability bits. So if you have more number of reliability bits, so we have more number of thresholds, so accuracy is higher. And usually most of the SSD fake use 4 reliability bits for ideal performance. So this is a hard decision where only one bit is generated for giving the information about threshold, which is this. That's only one threshold, and it say whether it's 0 and 1. But in the soft decision decoding, you have multiple bits, so you have multiple threshold. And instead of saying that it's 0 and 1, it says that what is the good probability of 1 or 0, or low probability or moderate probability, depending upon received signal. And so soft decision decoding create better accuracy. So these are the some of the fake. I tabulated it here from the generation wise. From these two are non-coherent fake from 10G and 10G4G. It's initial what we call first and second generation of fake, and you can see these are the hard decoding fake. You can see the overhead. You can see the net coding gain, prefake bar. You can see the prefake bar is very low. Means required bar level should be very low, otherwise fake won't work. So it wasn't very effective. But the coherent one, you see we move to the soft decision also, and the required bar threshold is very high. Means even there is a high bit error, still the fake can work. Um, One of them, which is mostly used, is turbo product code or LDPC code. Uh, which is basically I'm not discussing the more mathematics and more detail about it, but it's interesting, like it's just a Hamming code in 2D fashion. So you have the data, and you have error correcting code in 2D fashion or in the 3D fashion, and then you run a loop through row and column and in the third dimension to try to detect the error. And since you have more error correcting codes, so more chances of detecting the error and more chances of correcting the error. So the turbo product code work very efficiently. It can give a very good accuracy, very low bit error, but at the cost of adding many extra bit. So this is one of the data sheet you can see for 100G in Acacia. You can see it's 15% overhead, 11.1 dB net coding gain, etc. You can also see what is the error after the fake. It's very low. And so on. You can see what is the coding gain, etc. for different fake. For also you can see that hard decision decoding doesn't work good. Penalty is higher for hard decision decoding, and soft decision is lower. The next one, I tabulated most of the modules which we use and what kind of fake SDSD and etc. What kind of net coding gain they have, what is the prefake threshold, and what is the overhead. And you can see, interestingly, this is the latest one, which support 140 gigabit or 1 gigawatt or 1.2 terahertz, 2 terabits. And this module actually use only 15% overhead. And later we see that why it has lower overhead than even others has 27%, etc. So we'll see it later on in later slides. But this is all about the fake. If you have any question, you can ask before I move to next topic. Okay, so I assume there is no question. So you can see that both in transmitter and receiver side, the DSP is heavily used and it impacts the performance of entire system. So DSP speed is very important. That's why we add more and more algorithm, more and more functionality in the DSP. So we need more and more bigger size. We need more and more bigger heat sink, dissipating the heat and etc. So size of the transceiver also changes accordingly. Okay, so next one is recent modulation techniques. So far we have discussed about coherent modulation techniques or higher order modulation techniques. We discussed about QPSK, 16-QAM, 8-QAM, how they look like, which one is preferred, star or square QAM, etc. And we have seen that what is the impact of nonlinearity, dispersion, and other noises on this higher order modulation. But why we need to move from this higher order modulation to other modulation format, we are going to discuss this here. So we know about something called higher order modulation, and higher order modulation is usually called 4D modulation format, because each modulation format in higher order modulation can be represented in INQ diagram, INQ. So there is 2 dimensions, so it's called 2D. And each modulation formats or each signal can be transmitted over different polarization. So information can be sent over X and Y polarization. So we have another degree of freedom. So 2 more degrees. So we have from 2D, so become 4D. This means we can send 16 QAM in X and or any higher modulation format in X and Y polarization. So two IQ and 2 orthogonal polarization become 4D modulation. So all the higher order modulation formats are usually used in 4D modulation in most of the transceiver. So if you check about Acacia or any other transmitter, you can see that it's always written DP 16-QAM or DP QPSK, DP for dual polarization. So you always transmit 4D modulation format. And if you check the 4D modulation format spectral efficiency, it's always even. So for example, BPSK, bits per symbol, supposed to be 1, but since we transmit both polarization, so bits per symbol is 2, not 1. Similarly, QPSK become 4, 8-QAM becomes 6, 16-QAM 8, and so on. So bits per symbol or spectral efficiency of 4D modulation format for because of 2 different polarization is always an even number. And why it's a problem? Sometimes it's become a problem because the spectral efficiency or bits per symbol is always even number, and we know that if you move to higher order modulation format, you have more effect of nonlinearity and noises because the symbol are becoming close to each other. So effect of noises, nonlinearity, distortion will be higher and higher. So OSNR sensitivity will be higher, required OSNR will be higher, and so it limit the transmission distance. So there is always a trade-off, always a optimization between which modulation format you use or what capacity you want and how much distance you can want. So for example, if you're designing a network, you have always an issue with OSNR. There's because of the bad fiber, because of some noises, some attenuation, etc. So the network is OSNR limited. So if you're designing certain fiber and you want to design, for example, more than 3,000 kilometers, so best option is to choose BPSK because it required OSNR to log this BPSK transceiver is very low. So in the longer link, you can actually implement BPSK. But if you bring back to the lower distances and you want to increase the capacity, so you can use QPSK because required OSNR is a little bit higher, and so shorter distance it can achieve that OSNR and so on. So there is always a trade-off between, let's say, capacity or spectral efficiency versus required OSNR or transmission distance. But in certain scenario, we reach to a scenario, for example, let's say we need to design a network of 2,500 kilometers. So if you see this plot, 2,500 kilometer, we can't use, we can use either QPSK or BPSK. Now let's say in 2,500 kilometer, the OSNR available in the link is very low and it's lower than QPSK. So you can't actually use QPSK. But let's say if it is higher than BPSK, so of course you can use BPSK, but you want to transmit more and more data, more and more symbol data, or let's say more spectral efficiency, more capacity. So you try to move from BPSK to QPSK, but you can't move because the OSNR available in the link is very small, not so that it can reach to the threshold of QPSK. But you need to somehow reach to 2,500 kilometer. So you are forced to move to BPSK, even though you try to go to higher spectral efficiency because there is no other option, and so on between 8-QAM and QPSK and so on. So if because the graph look like steps because after the BPSK only next available option is QPSK, so you can't implement anything in between. Even though OSNR is higher than available OSNR in the link is higher than BPSK, you can't move to QPSK because of this limitation. And so the gap is too high. So if somehow we can provide an alternative between these two higher order modulation formats, So our spectral efficiency is even number, and if we can provide a number between two even number, odd or fractional number, so we can fulfill those scenarios where the OSNR is better than implementing BPSK but lower than implementing QPSK. So still we can move to better performance of the system, or let's say optimum performance in a given network if we have option available between BPSK and QPSK. And that's why we need to move from on the 4D modulation format or higher order modulation to next level. So we need to go to the place where a spectral efficiency is not even number for 4D modulation, but instead either odd or fractional. And Acacia actually support this. Acacia support 1 to 6 bits per symbol per polarization. So this means it can go either odd number like 3579 that to using set partitioning method, or they can even go to the fractional number for up to difference of resolution of 0.1 bits per symbol per. So that is possible by time domain hybrid modulation format, and both of this is supported by Acacia. And of course, if you move to that, you have certain gain. We can see later on. So first we go to set partitioning modulation format. So remember, like if you use 16 QAM in dual polarization, you have 4 bits per symbol for every polarization, so you have total 8 bits per symbol. And so if we don't want to use 8 bits per symbol, we want to reduce it to odd number. So what is the lower odd number other than 8 is 7. So we want to make 7 bits per symbol for DPE 16 QAM. This means we are going to use only 7 bit and 8 bit we need to discard. And how they do it, they actually take all the 7 bits and they don't use the 8 bit for information, rather than they create certain logical function based on the 7 information bits. So effectively, they don't use the 8th bits. And so effectively, the number of bits per symbol for DP16 QAM become not 8, but 7. This means the symbol which was number of symbol which was 256 is reduced to half, 18028. And this is called set partitioning modulation format. It's supported by Acacia 1200 and it's available there. Now, what is the use of this 8th bit, which is not information bit? So 8th bits can use to improve the OSNR performance. So for example, this is the two different polarization X and Y, and this is the 16 QAMs. So now which we have 256 symbol, but we need to discard 128 because the last bit we are not using. So which 128 bit need to remove, or which half of the bit symbol we need to throw out. So they decide, like, for the best performance, if you choose a diagonal one rather than the adjacent symbols, it will give you the better performance in terms of nonlinearity. So only either red or black symbols are used, and other half of them are thrown away in a way. So distance between the symbol, basically, instead of this, it becomes this. So it's increased by √2 times. So the performance in terms of nonlinearity and distortion improve. And since the performance in terms of noise is improved, so OSNR penalty decreases, and required OSNR at the threshold level at transmit and the receiver end also decreases. So when we move from 16 QAM, DP16 QAM to SP, half of the removing half the symbol, basically we try to improve the OSNR performance. And so we can transmit it for longer distance, or to the distance where, or to the network where the OSNR level is low. So even in that case, we can use the 16 QAM. Similarly, we can use for QPSK. So in the QPSK, you have four symbol in every this not symbol. There is a total 16 possible symbols, but these are the combination in X and Y polarization. So last one, again, we use only 3 bits, so total 8 symbol, but the last bit is not used for information, rather than used to create this removing the additional half of the symbol. So again, it's diagonal which is used. Another way of doing the same is instead of removing this two, we can decide either to choose one of the polarization without symbol, another with the symbol, and do it alternatively. So we send full QPSK in one of the polarization, don't send any symbols in others polarization, and we can do it like alternatively. In this way, we can throw away the half of the symbols. So in that case, it's called polarization switching QPSK, because alternatively we switch the polarization. So 2 bits we use to encode the data, and the 1 bit, the third bit, we use to switch the polarization. And that's how we achieve the polarization switch. QPSK, or another word is called set partitioning QPSK. Okay, so while we're doing so, what we obtained is initially we have only BPSK or QPSK or 8-COM, 16-COM, etc. But while doing the set partitioning, we create another level between the BPSK and QPSK, and that's called Horizon Switch QPSK. And similarly, between any two 4D modulation format, we try to create another level, and that means we are trying to create a odd number of spectral efficiency, or odd bits per symbol for 4D modulation format. Since the it's create another label means you have now option to not choose BPSK but choose a better one. But since OSNR is not good for QPSK, so you can go between BPSK and QPSK to have a better performance or optimum use of resources, whatever we have in the real link. So that's why the SP or set performance partitioning modulation format came, and Acacia has started to use it in their module. Next one is hybrid modulation, which is even more interesting than set partitioning. And eventually, the mostly used is hybrid modulation in most of the transceivers. Okay, any question? I hope it's clear. If not, you can ask me. I hope I'm not discussing.
Yeah. Hello. I have one question. Oh.
Yeah.
Yes, we learned such method of modulation. Yeah, but I want to ask, so many modulation approach or method, are they all patent proprietary or open to everyone, like Nokia, Huawei, and us? We can all use this, or that we cannot use this new technology. So.
It's open to everybody, but I will show you in the probabilistic modulation what is proprietary, and they don't disclose. So Acacia even also. So next one, when I go to probabilistic modulation shaping, there I will discuss that. I mean, the technology is well known, but what they do inside the DSP, they don't reveal it. So idea is well known, and idea is available to everybody, but every company has their own propriety to how they convert the bits. So I will show you when we come to probabilistic modulation.
Okay, thank you.
Otherwise, hybrid modulation and all set partitioning is well known, and everybody use in a very similar fashion. Okay, so let's understand what is hybrid modulation. Hybrid modulation basically can provide even the spectral efficiency of fraction. Means not only odd or even, but it can go 2.1, 2.2, whatever is your requirement according to available OSNR in the link. So you have more flexibility of choosing the modulation format depending upon your real network. So if you see how the higher order modulation works, so we have a bit stream coming up, and we make it like serial to parallel converter, and then make it select the 2 bits. For example, QPSK require 2 bits per symbol. So select the 2 bits for every polarization. So 2 bits per symbol is select, and it's kind of grouping it. So in that symbol duration, it select to 2 bits, and so on. So you select 2 to 2 bits. And for every symbol, you try to transmit those symbols. So in a series of time. So for example, transmitting 0, 1 is transmitting this symbol in this constellation diagram. So and so on. So whatever the next one occur, it transmit that one. Next one occur, transmit that one. Transmitting the constellation diagram means you're transmitting with certain phase and amplitude. So with that phase and amplitude, okay. So so higher order modulation basically group the bits, create the symbols, and transmit those symbols as a series of time. Now, how the hybrid modulation work is instead of sending all the bits with the same modulation format or same constellation diagram, it send different bits with a different modulation format of transmission or the constellation diagram. So when the bit stream comes, so what the time domain hybrid modulation do, it selects certain bits to decide to send it through the QPSK. The next bit it will send it through the BPSK, and so on. Alternatively, it can be different combination as well. So what does it mean that the first 2 bits is transmitted according to QPSK, next bit it transmit according to BPSK, and do alternatively. So in a way, if you check in the time domain, you have the spectral efficiency of 2 and here is 1. So average is 1.5. So instead of 2 or 1, it achieves fractional spectral efficiency because it tries to send alternatively higher and lower modulation formats or higher and lower spectral efficiency. So in this case, it's 1.5, but you can have various combination. You can send 2 QPSK and 1 BPSK in a series of time. And in that case, you can achieve 1.7. Or if you can send 1 QPSK, 2 BPSK at a series of time, alternatively, then you can achieve 1.3. So you can play around how many symbols you are going to send in certain modulation format, how many in other modulation format, and basically you can create a very fine resolution of a spectral efficiency. Usually Acacia play in the same way and they can achieve 0.1. We use usually in between the two. So if you define the spectral efficiency, so it depends upon how many number of symbols you are sending in certain spectral efficiency and how many in other. And in this formula, you can try to find out what is the effective spectral efficiency. Now, effective spectral efficiency means required OSNR will be also combination between these two modulation formats. So required OSNR is also changing. So you achieve in between lower and higher modulation format, required OSNR at a transmitter. So you relax the OSNR requirement as well when you do the time domain hybrid modulation. And that's the concept of using it. For example, if you need 4.8, so 60% of time you send QPSK, 40% of time you send DP ETCOM or ETCOM, and this combination generates a spectral efficiency of 4.8. Now there is some rules which modulation format to choose for the time domain hybrid modulation. And usually the closest modulation format, for example, QPSK and 8COM is chosen, or 8COM and 16COM is chosen. In general, which two modulation format are chosen where the required OSN are very close to each other. For example, if you choose QPSK and 16COM, the required threshold at the receiver will be very, very different, very, very far away, and it may not be able to achieve. So error will be higher. So they choose very close to each other. For example, here PSK and 8COM or 8COM and 16COM. So that's one of the rule. Most of the Acacia also follow this rule. And the second issue is power. What power is going to transmit in this QPSK and what power is going to transmit on 8COM. And it's a big issue because the power is going to determine the nonlinear performance. Now, every modulation format has its own characteristics in terms of nonlinear performance. So this one will be less affected, this one will be more affected. So whether you choose here low or here more, what power ratio you're going to choose. So we define it as a power ratio of two modulation format, and this power ratio basically affect the transmission, affect the system performance, bar, and etc. So there are different strategies to follow. So either you keep the same power ratio, means the both modulation format have the same signal power. In this case, the power ratio is 0 dB, which is very bad because the lower one will lower value of power will go be almost error-free transmission, and higher power will go through uh, higher one go through, or higher modulation format will go through more error. So this is not very preferable strategy to keep the power ratio 1. So next one is choose the power ratio depending upon the distance between the symbol. So let's say distance between the for QPSK is D1, here is D2. So try to choose in that ratio the same power. The power ratio is also equivalent to the ratio of this. Another one is to choose the power ratio according to equal burr. For both modulation format at the end will have the same burr. So choose the constant power ratio according to equal burr. Another one is choose the modulation power ratio according to the minimum target burr. So in both cases, this is the minimum burr required for them to lock. So choose the power ratio accordingly to achieve those minimum target burr. And they try to do simulation and as well as measurement. And they found that if you, let's say, for example, if you use QPSK and 16COM, which is not preferable because it's far away from each other, but for example, if you check 50% QPSK, 50% 16COM, the resultant should be in between, so it will be 8COM. So they try to use 50%, 50%, and try to use different power ratio strategy, and they found that the power ratio, which was 0 dB, has very bad performance, while other three has very similar performance to 8COM, which suggests that you can use this power strategy. Now, this power strategy, what they use at the transmitter is not known. They don't reveal. So this kind of information the companies don't reveal. All the technology is known that what is hybrid modulation, but these are the information which are sensitive. They don't reveal which one they use. This is another example. So here also another way to choose the modulation form, hybrid modulation, is the effect of frame length. Like what is the number? What are the number of symbols you use? Larger number of symbols you use in any hybrid modulation or any certain modulation format, the impact of nonlinearity will be higher. So they try to reduce the impact of nonlinearity by choosing the smaller number of symbols for each modulation format. Another one is like if you transmit the both polarization with the same modulation format, the effect of nonlinearity is more. So they switch the modulation format when they switch the polarization, and they use alternatively in terms of polarization. In this case, it's called polarization interleaving, and effect of nonlinearity is very lower. So these are the strategies they use to make it effective. And if you do that, so if you remember the hybrid modulation, the higher order modulation have only even number of spectral efficiency, and set partitioning has now odd number of spectral efficiency. But when you do hybrid modulation, you have a smooth curve. You can generate as much lower as possible. So with a granularity of 0.01 spectral efficiency, you can achieve. So, but in practice, you can achieve anything. And also, what combination you choose, of course, what number of symbols you use for each modulation format. But basically, you can obtain this curve. Means now you have more and more available option to choose the modulation format depend upon the available OSNR in the link, and you don't need to stick to only few modulation format. So you can optimize the entire network depend upon the real OSNR available in the link, and that's the benefit of hybrid modulation, and that's why it came to all the most of the commercial transceivers. And Acacia 1200 is same. It's just a block diagram. They do provide the same. They can move from one to other, lower to higher baud rate, according to so for example 28 to 69 baud rate according to the modulation format they choose, higher modulation as well as the hybrid modulation. Okay, so here, for example, you can see it's 2-bit per symbol. They can generate 2.5 bit per symbol, depend upon the combination they use at common QPSK. They can go for 2.75 bits per symbol, again, which different combination you use. And you have this option to choose through the software what you want to define. Okay, that's the hybrid modulation. I hope this is clear. Any question you can ask now?
So hi Abhishek. So are we using this kind of modulation in any of our card?
Yeah. In
And
AC1200, you have this option to choose.
okay.
So you can choose like 2.5, 1.5. Yeah, you have these
Okay.
options. Yeah.
Okay. It will be available after to AC 1200 only. Below this we don't have
Yeah,
to switch it.
if you go to configure the card, there is some command where you can choose this bits per symbol. Yeah.
Okay, correct. Thank you.
Okay, next one is constellation modulation. Constellation modulation is interesting concept to increase. It provide more and more option, like same the smooth curve, but also it increase the capacity. Although it came in many conferences, but it didn't succeed to the commercial. It didn't come to the commercial level. So I will skip this here. But I will just introduce a little bit, not more, because it's not currently used anywhere. So what it does basically, so instead of um, hybrid modulation, choose different modulation format as a series of time, so achieve this finer spectral efficiency. But what the constellation modulation does, it not only it transmit different modulation format with a series of time, but also it use some bits to encode the data that which modulation format to choose. So for example, if you have a pool of 4 modulation format, so it use some of the bits information to choose which modulation format to use, and then use those modulation format again to transmit the symbols. So for example, here, so your bit stream comes, so is divide two bits to choose which modulation format to choose. For example, here QPSK, so it's choose the 01 is correspond to QPSK. So it's take that one and then select certain amount of symbol from it. So 00 it encode into the QPSK. The next one is 00 here, so it use this to select which was belong to 00, so it's belong to BPSK. So it's use this 00 information to select the BPSK and then actually encode next next bits into the symbols there. So basically, it has another degree of freedom, not only the phase, intensity, and polarization. It uses modulation formats itself as another degree of freedom to encode more and more data. So basically, it's increased the spectral efficiency more than other modulation format, but it's also increased and also can provide the fractional spectral efficiency. So it's more flexible, but it has many limitations, and they found at the end. So I'm skipping all this because it's not useful. They found at the end that it's not mostly useful for BPSK, close to BPSK. Other cases, the spectral efficiency increase is not very high, and that's why it was complex DSP. So they abandoned this, and it never come to the commercial. Okay, next one is interesting. It's called probabilistic modulation. Okay, so far we have seen that our main aim is to transmit more and more data, transmit more and more capacity through the fiber for long distances, or let's say error-free. And how we achieve it? So to increase the capacity or data rate, we improve the spectral efficiency, total capacity, or let's say capacity of a channel. Total capacity is number of channel into this, but let's say capacity of a channel is bits per symbol, that is spectral efficiency times symbol rate or baud rate, what we call, plus fake overhead, the fake we always add. So to increase the bit rate, either we increase the spectral efficiency, so or we can increase the baud rate, and in both cases we can increase the bit rate, overall transmission data. So when we try to increase it, what we face always a problem is capacity versus transmission distance. There is always a trade-off. If you want to send more and more data, it won't go to the higher distance because of the dispersion, nonlinearity, and other all other effects start to play, and it reduces the OSNR, and so required OSNR threshold at the transceiver rate increases, and so you cannot transmit for longer distance. So there is always a trade-off between capacity or the bitrate versus the OSNR or transmission distance. So first method we used when we saw that to increase the capacity, you increase the spectral efficiency. So we move to the higher order modulation format. But as long as you go to higher order modulation format, the distance between symbol decreases. So effect of distortion is higher. And so OSNR penalty is higher. So if OSNR penalty is higher, means required OSNR is higher. And in order to lower that, we use fake. Once you use fake, of course, we lower down the OSNR penalty or required OSNR, but then we are reducing the actual information carrying capacity. So fake overhead comes at the expense of reducing the information capacity a little bit. So second method, we'll not discuss this here, but the third method is set partitioning or hybrid modulation. We saw that there is a play of how to choose OSNR, and we don't have option. So we move to set partitioning and hybrid modulation, where we can send to the relatively longer distance at the cost of reduction of little bit capacity. So instead of choosing the QPSK, we choose set partitioning or low hybrid between BPSK and QPSK. So it is actually we play around little bit reducing the capacity, but we gain in terms of OSNR or transmission distance. So we have more flexibility. The another method is you can just increase the symbol rate. So if you increase the symbol rate or baud rate, your bit rate overall capacity will increase. So once you increase the symbol rate or bit rate, baud rate, what will happen is the effect of nonlinearity will be higher at higher symbol rate. So again, the OSNR penalty will play. So even if you go to higher baud rate, the OSNR penalty will be higher. So transmission distance is limited. So again, we use fake to overcome this OSNR penalty or reduce the OSNR threshold to increase the transmission distance. And then once you use fake, we end up in reducing the information carrying capacity a little bit, not too much, but a bit. So then we move to a new modulation format, which used in most of the new module is called probabilistic shaping or probabilistic modulation. So what it does basically, it increases the data rate by increasing the symbol rate. So if you increase the symbol rate, it will increase the data rate, but without causing additional OSNR penalty or increase in fake overhead. So having the similar fake overhead, but still it can increase the symbol rate and reduce the or continue the same OSNR penalty or even reducing the OSNR penalty. So what it does actually, we'll see in the next slide. So okay, so usually this is the way to transmit signal. So we have a bit stream, we make it as a symbol, combine it together, and use this symbol to transmit into the fiber. So group the bits into the symbol. That's the main idea. Okay, and these symbols, or these all the bits usually in the real channel comes randomly. But what is the probability of happening these symbols? If you group into the symbol, the probability of happening each symbols are very equal. So it's equal probable that this symbol can occur in the information or this or this. So any of this symbol, for example, in this case 16 64 any of this symbol basically can occur in the real traffic. So all these symbol can occur equally, but the effect of the noise on the symbol are not equal. So probability of noise distortion in each symbols are not equal. Some of the symbols are heavily affected by noise and distortion, and some of them are not. So probabilistic modulation, what it does is try to send only those symbol, or most probably those symbol which has lower effect of noise and the and the distortion. So probabilistic modulation is just try to create a method in which there is a more probability to send those symbol which has lesser effect of noise and distortion. And how it does, so it creates something called distribution matcher, DM. This distribution matcher, it take all the equal probable symbol and convert to the new symbols which has lower chances of having noise and distortion, and then it transmit it. So now we are transmitting all this symbol with converting into another symbol which has low chance of distortion. So we actually gain in terms of OSNR penalty. So we have lower OSNR penalty, means required OSNR threshold will be also lower. So effect of distortion will be also lower. So fake overhead is not increasing. So if you go for higher symbol rate, still we can have a lower and almost no increase in fake overhead. And that's the benefit of probabilistic modulation. So for example, here, instead of sending all the symbols, they send these symbols which has lower chances of distortion with the higher probability. It does set other symbols as well because there is no way of controlling it, but with lower probability. So overall, there is an improvement in the OSNR performance. And for that, what it does, it takes the data and pass it through something called distribution matcher, and then pass through the fake encoding and everything is same. And at the end of receiver, it has inverse distribution matcher to get back the original symbols, original data. And this is the propriety of most of the vendors. So most of the vendor, they never disclose how they converted the original symbol to distribution matcher. Although this technology is well known, there are a lot of literature about it, and everybody have a different method. They don't disclose it. Even I try to ask Acacia, but they don't disclose how it convert, what logic function they use actually. So if you see the improvement, so if you have a fixed transmission distance, you can see that you can increase the data rate without even changing the fake. So even you can see the 15% increase in the data rate without changing the fake. Or if you have the same data rate and you can improve the 40% distance without changing the fake. So that's the improvement in terms of 16 QAM if you use 16 QAM as a probabilistic shaping. And this is the region these modules can support up to 140 gigabaud, very high baud rate, because it uses probabilistic shaping. And if you see the fake overhead in the slides, it has not very high fake overhead as compared to other modules. So a second. So here you can see it has only 15% fake overhead rather than going too high. So usually Akasha 1200 has 27%, but here in this module it has very low because it used the probabilistic modulation. Okay, so this is the probabilistic modulation, and so this is a summary of all the modulation format, what is the OSNR requirement, and transmission list, and all the methods, and all the usual thing I mentioned here as a summarization. So that's all about the recent modulation technique, but if you have any question, you can ask. A few more slides to go. I hope it's not too detailed, or almost there is no mathematics, so it's not. I hope it's not difficult to follow. Okay, so I'll just go quickly over the future modulation format, which might come not right now, but either it's coming or it will be in the future. One of them is OFDM. OFDM is there's a lot of noise about it in many conferences, So if you see that number of why the fiber capacity is limited, because you have limited number of channel, and we have a guard band between the channels, so we can use limited number of channel in C and L band. So if you want to increase the capacity, if we can squeeze the individual channel in a way that we can overlap them, then we have more and more number of channel and more number of capacity. But if you overlap, you have overlap of information and you cannot recover. And so OFDM do the same thing. It overlap the different channel in orthogonal frequency domain. So it's look like in frequency domain is overlapping, but it's like a cos and sine function of different channels. So it never overlap actually. And you recover the same with something called FFT and IFFT filter. So you can recover this overlapping symbol without causing much bit error. So that's the benefit of OFDM, that you can increase the capacity by huge amount. Uh, but there is a lot of problem because it's very sensitive to phase offsets and so on, and it's very electronically complex. So it's require very complex DSP, speed of DSP, as well as heat sink problem, and etc. So that's why it's so far it didn't come as a commercial in a commercial vendor. This one is interesting as a special division multiplexing. We don't use it, but recently it had been used for some submarine communication. They started to use there at least. It has been used for Metrolink in data center applications. So I'll go quickly over it. Maybe interesting, but not very useful for current. So we use usually what is called single mode fiber, which has very small core. So only one mode can transmit. So it's called single mode fiber. It has very small attenuation and dispersion is very small because it has only single mode. So this is what we use so far. In the past, we used to have something called multi-mode fiber where core diameter was very big. So it can accommodate not only one mode, but multiple modes. And since then, multimode modes, we have another source of dispersion called multimode dispersion, so we cannot overcome it, and that's why in the initial days it was used in early 200 or late 80s 90s, but then it was discarded because of the PMD, not PMD, sorry, because of multimode dispersions. It is still used for campus and data center where distance is lower, so dispersion effect is not too high. So still in use in certain places, but it was discarded in the past. But now people have started to pay more attention towards it, because even we have a model dispersion, we can eliminate this dispersion in DSP because you have now powerful DSP. And those days there was no powerful DSP. So we can use the digital signal processor to remove the model dispersion. And if we are able to remove the model dispersion, means we get rid of the problem and you can use multiple modes. So now we have multiple mode, not only single mode. So in the single mode, whatever we can transmit C and L band, we can multiply by m times. For here is 4, so 4 times. So you can increase the fiber capacity by 4 times, in general m times. And that's the benefit of the multimode fiber, that it increase the overall capacity multiple times as compared to single mode fiber. And that's why it paid a lot of attention, and they started to develop the ecosystem for it. So they have now multiplexer, demultiplexer, ROADMs, amplifier, etc., everything in multimode domain. And they can implement this in multiple ways. Either it can be multiple fiber all packed together, or it can be multiple core, single fiber but different single mode cores, or it can have single core but multi-mode core, or it can have multiple core with multi-modes. So these are the things special division multiplexing support. So basically, it can multiply the fiber capacity by multiple amount. And recently in Finera last year demonstrated it, transatlantic cable with the real-time traffic, and they have successfully shown that. So it's already almost came to the submarine link, this technology. It might come. Quantum, we know that we are in India also, we have started to work on QKD, and it's also making quite progress. So next coming years, it's almost $1 billion market. Already there are many companies in US and China are working on it. Already deployed the network for more secure communication, like financial institution and stock exchange, etc. There are some major players started to work in this direction. So this might come very fast in future. So these are all. If you have any question, you can ask. Okay. So if no question,